Welcome to Math Made Easy. Now, think about this shape for a second. You've probably seen it thousands of times, but have you ever really looked at it? Today, we're going to dive into the hidden geometry of the egg, and it's a fascinating journey from a simple curve to one of nature's most perfect designs. You know, the shape is so familiar that we just take it for granted. But hiding inside this everyday object is a really cool mathematical and evolutionary puzzle just waiting to be cracked. And yeah, this brings us to the big question. It seems almost childishly simple, doesn't it? But the answer reveals this beautiful intersection of math and biology. Why this specific, kind of weird asymmetrical shape? Okay, so to understand the egg's unique shape, its asymmetry, we first have to start with a shape that's perfectly symmetrical. Let's kind of build this thing from the ground up, starting with one of the most elegant curves in all of mathematics. Meet the ellipse. Just think of it as a perfectly stretched out circle. It's defined by a pretty simple, elegant equation. And as you can see, it is perfectly symmetrical. The top and bottom are mirror images, and so are the left and right sides. Just keep that perfect symmetry in your head for a second. So let's jump into the third dimension and see what happens. If we take our flat 2D ellipse and we spin it around its axis, it carves out this 3D shape called an ellipsoid. Now, this seems like it should be our egg, right? It's smooth, it's curved, but it's still perfectly symmetric. And this is where it gets really interesting. When you put an ellipsoid next to a real egg, the difference is just obvious. An egg is asymmetric from top to bottom. One end is pointier and the other is blunt and round. So an egg isn't just a rotated ellipse. No, it's something way more clever than that. So if it's not an ellipsoid, what is it? Well, lucky for us, mathematicians have been studying this for centuries. And it turns out there really is a universal formula that can describe the perfect egg shape. And here it is, one of the most famous solutions, the Hoocher Egg Curve. Now, don't get intimidated by the math here. The secret ingredient, the real magic, is right here in the denominator, that little c times sine of t. That tiny tweak is what breaks the perfect symmetry and creates the egg's classic pointy end. So here's how that little c parameter works. Think of it like a dial. If c is 0, you just get a perfect symmetric ellipse. But as we start to turn up the value of c, the shape gets more and more pointed. And for most bird eggs, a c value somewhere between 0.2 and 0.3, that gives us that familiar perfect shape. Isn't that wild? One single number controls all the eggness? Okay, so we have the what, we have the formula. But you know, that just leads to an even more interesting question. Why? Why did millions of years of evolution settle on this specific mathematical form? This definitely wasn't an arbitrary choice. Nature's genius is just on full display here. First off, you've got safety. If an egg on a cliff edge gets knocked, its weird shape makes it roll in a tight circle, not straight off the edge. So smart. Second, strength. That double curved dome is incredibly strong, evenly distributing the weight of a parent bird. And finally, efficiency. The pointed ends let all the eggs nestle together like a perfect puzzle, which helps conserve precious warmth. So we've got the formula and we've got the evolutionary reason why, but what does this perfect shape actually mean in the real world, and where else can we find it? Well, just how much fits inside this perfect little package? The volume of a standard chicken egg is about 65 cubic centimeters, which is roughly the same as a shot of espresso. And the surface area, you know, the amount of shell needed to contain all that goodness, it's about 70 square centimeters, or roughly the size of a credit card. This really reveals the brilliant trade-off at the heart of the egg's design. See, a perfect sphere is technically the most efficient shape for holding volume, but nature sacrificed a tiny bit of that efficiency to gain enormous structural strength and safety. It's just a masterclass in natural engineering. And of course, we humans have learned a thing or two from nature's design. We use egg-shaped domes in architecture for their amazing strength, and engineers use those same curves for high-pressure tanks. This optimal shape is truly universal. It shows up in everything from tiny plant seeds to massive asteroids floating in space. So we started with a simple question about a shape in our kitchen, and we ended up with a universal mathematical formula that was perfected by evolution for strength, safety, and efficiency. It really